First serious technical literature describing Mars transfer vehicles was done by von Braun in 1949, German book Das Mars Project. The first NASA-funded mission studies of Mars missions was done in the early 60s. The Empire studies was done by 4 different contractors in the early 60s. So that's when the ball got rolling describing Mars transfer vehicles. Von Braun's team was preparing for a follow-on mission to Mars after Apollo. In the summer of 1969, he and the Marshall team and the NASA team presented to Congress a Mars mission with a vehicle design. Of course, that wasn't followed through. During that period in the late 60s, an engine specifically developed for Mars transfer was being developed in Jackass Flats, Nevada. That was the Phobos, Rover, and Nerva class of nuclear engines. They actually tested full-up engines and almost perfected that particular type of propulsion. That was concluded in the late 60s, early 70s. And during the late 70s, there was a period when there wasn't a lot of study of Mars transportation systems was going on. Then,
just say next slide.
Okay, well, this is my introduction, so I can say next slide, okay? So, then in the 80s, about mid-80s, there was another renewed interest in Mars transportation vehicle design. That's when I came on board for Boeing in the late 80s. We had like a 4 or 5 year contract with NASA Marshall to develop space vehicle concepts just for human Mars missions with precursor lunar missions. So we had 4 or 5 years studying in very detailed fashion what the lander would be, what the air brake would be, what the transportation would be, what the launch vehicle would be to put it up, how you would assemble it. So there was a lot of studies done in the late 80s and early 90s, and so we're back doing that. So we have maybe 40 years of conceptual design of Mars vehicles to look back on, and probably I'll get the chance to talk a little bit about history. But my particular section, and I'm glad I can follow these because they've set up this pitch very well, is really the Earth-Mars transportation system. What is the vehicle? How would you get it up there? How might it fly to Mars and back? And what are the lander systems? So I'm going to kind of devote myself exclusively to the technical challenges of Mars missions. And as Brent described earlier, there's a big difference between a Mars mission and a lunar mission. Perhaps for a lunar mission, you're only 3 days away from returning back to Earth. But if you embark on a manned Mars mission, you could be as much as 2 years from return. So you don't have immediate return, and you have to design a vehicle and a habitation system that is consistent with that. And there's the tension between developing low-mass systems that don't require as much mass to launch and highly reliable systems. The more mass you have, the more reliability you can have. So there's always a tension between how you design the vehicle. And so there's got to be a balance between the reliability that comes when you have enough mass and then the lower launch costs that would come when you reduce the mass. It costs less to launch to orbit. There are basically 4 different types of propulsion technologies I'll touch on here in the next few minutes. How you might get from Earth orbit to Mars orbit, and that would be the solar electric propulsion system, the nuclear electric propulsion system, the nuclear thermal propulsion system, and the 4th would have been the chemical propulsion with air brake at Mars option. So 2 of those are high thrust, 2 of those are low thrust. And those are different animals altogether. How they fly is going to be different. How you operate them is going to be different. So I'm going to just scratch the surface, talk about these 4 different candidates, and try to make some sense out of what we might choose to do if we were going to design the transportation system for Mars. Next chart. All right, I'll start with the SEP, Solar Electric Propulsion System. And this represents the ultimate, as General Bolden said, want to go to Mars. And so this represents a large solar electric propulsion system with a power level consistent with fast trips to Mars. That would be about 1 megawatt. But that would be, in a stair-step approach, that would be the last in a series of smaller transportation systems. Okay, and so we talk about a 200 kilowatt, a 400 kilowatt, and then finally the 1 megawatt that would get you to Mars. And so what you can see is inflatable crew habitat at the front with a Earth return vehicle for the return to Earth later. This 1 megawatt system is dominated by large solar arrays. We'll talk about that. And then next chart. On the back end would be the propulsion system, Vasmir or concentric hall thrusters or Lorentz force thrusters or ion thrusters. Low thrust systems that will thrust continually on the way out. The difference between a high thrust and a low thrust, a high thrust system would perhaps thrust for 2 hours departing Earth, and it would coast the remainder to Mars. So about 200 days would be coasting. For the low thrust system, SEP or NEP, would be thrusting almost the entire time, so those thrusters would be on for 180 days. So that's part of the difference between a high thrust and a low thrust. One is continuously operating. And so this vehicle would be continually thrusting. The vertical arrays would be the thermal radiators, and the bigger arrays are the solar radiators. And so the SEP has received a lot of attention recently because there's been progression in solar arrays and cell efficiency and the packaging efficiency of those. Just there has been some advances in electric propulsion technology recently with the Vasmir thruster, with the concentric Hall thruster. So the propulsion system and the power system have seen efficiency gains in the last few years. And so you apply those gains. That's why I wanted to start with the SEP as the first. Okay, so this represents 1 megawatt power system. That power level is chosen because of the trip time that you want. You want a trip time in the range of 180 to 200 days outbound to compete with the other particular systems. All right. We would also like a flexible path architecture because that SEP vehicle is potentially as long-lived as a commercial satellite. It might live 15 years, potentially. And so if you have a Mars mission, you could bring that vehicle back and reuse it for subsequent missions. All you would have to do is resupply its argon or xenon propellant tanks, bring up some more crew consumables and another crew, and you could repeat that mission or fly to another destination. So if you had a vehicle that was inherently reusable, then you might want to set up an integration node at a high Earth orbit, like L1, Earth-Moon Lagrange point, so that when that vehicle returns from Mars, it can park at a high Earth orbit and not have to go deep down to the Earth gravity well and come back out. And so if you had a flexible architecture and you had a vehicle suitable, you could use it for a variety of missions. Go to NEO, go to lunar orbit, go to an asteroid, and then go to a low lunar orbit or go to Phobos. And so that vehicle or that series of vehicles can be reused for a variety of missions. And so you might begin the vehicle in low Earth orbit. Perhaps these big 1 megawatt SEPs would park near the station. They're too big to attach to the station. But parking them near to the station, and then when you deploy the arrays, you might need some astronauts to assist the deployment. And so because it's close to the station, it could be a helpful integration node. Then it can fly up under its own power to L1, and then the crew can come up later in a chemical stage, rendezvous at L1 at that station, and that vehicle can depart and return to that destination, that high Earth orbit. And so you might have a cycling vehicle that goes between low Earth orbit and L1 to provide propellant or consumables or other items that the crew might use. And so you're defining a flexible path architecture in which Mars is just one of the destinations, and it might be the biggest and latest of the SEPs that we described. L1 is quite a bit of a ways out. It's near the moon. It's only 600 meters per second away from low lunar orbit. And so what you do is you save the vehicle when it comes back to Earth the task of going deep back down to the gravity well, and saves you a lot of propellant, and you don't have to pass through the Van Allen belts again. So L1 might be a good place to stage the vehicle. Here's a picture of a conceptual vehicle. You can see the transfer habitat on the left, the big solar arrays, and then the cruise system. And that cruise system might be the upper stage of a heavy lift launch vehicle, LOX chemical propulsion. And that would boost the crew up in their multi-purpose crew vehicle to rendezvous in L1 for the subsequent mission. Now that SEP vehicle that I described would take several months to go from LEO to L1. And so the crew would come up later in a vehicle that would only take a couple of days. All right? As Brent already mentioned, there's a cycle in these Earth-Mars transits, and it turns out that 2030, 2033 are two of the easiest years that you can fly to Mars. As you can see, a hard year is 2041. So planning for a 2030, 2033 mission is a good target because it's an easy year to accomplish these missions. And so that's delta P, the energy requirement to get from Earth to Mars versus Earth departure year. And so we're targeting 2033, 2030 as an easy year to do the initial Mars mission. Right? One of the things that a low thrust system can do is it can approximate the trip time to Mars of a high thrust system if it utilizes an intercept rather than rendezvous trajectory. So we've done a lot of trajectory analysis, and one of the ways to match the transfer time of a high thrust system to try to get it down to 180 days, which is a short trip time, is to fly a vehicle out on an intercept trajectory. It's not going to rendezvous with Mars, but it has an intercepts Mars. The crew and their crew system and aeroshell are going to aero capture into Mars, establish an orbit, and that SEP vehicle on intercept trajectory is going to fly back to Earth, return to L1 for reuse. Their transfer vehicle for the return journey is already parked in Mars orbit. Matter of fact, you might have two. And so they're going to return with the same vehicle, same type of vehicle that has been pre-deployed. So you do like to pre-deploy assets at Mars so that you can give that crew that opportunity. So that's just one way of doing a Mars mission. A precursor to a Mars mission is use the same technology, the same arrays and thrusters, and maybe create a 400, 300 kilowatt vehicle and fly it to a NEO. A shorter mission than a 3-year mission. You try out the technologies. You don't need a lander to land on an asteroid, and so you don't have to carry along the Mars lander with this mission or this vehicle. So it's basically a smaller version of the Mars vehicle. It has the same thrusters. It has a crew habitat sufficient for the crew and the duration they're going to use. And therefore, you're going to prove out your transportation system in an incremental approach. And each time you grow the vehicle, it's just going to be a modular change. You're not changing the technology. You're just making several sets of it. So the Mars vehicle might be 2 sets of the 400 kilowatt power system. So you've proven the vehicle at an NEO mission, same technology, same vehicle archetype is going to be used for the Mars mission. So you go to Mars knowing you've already tried all the transportation architecture at smaller power levels. You also might use that same SCP vehicle to fly the GEO and service satellites. You could disposition satellites, move satellites, refuel satellites. And so there are a lot of assets in GEO that can be accommodated, serviced, or moved out of the way with the same vehicle. So I'm trying to paint a picture where you have one technology used in a variety of missions, and ultimately it makes it to Mars. And so by the time you leave in 2030, you've had a decade of use of that technology. It's not going to be a new thing. Okay, part of the reason that SCP is being studied, and I chose it first, is Boeing has an array technology called the fast arrays. There are 12-to-1 concentrator arrays. So it turns out that this particular technology has a very high packaging efficiency. It's much lighter than an array, a comparable state-of-the-art array, and it's radiation resistant. That is, it can take multiple passes through the Van Allen radiation belt without incurring much degradation of performance. So because of these attributes, we're choosing that fast solar array as the basis of our SCP evaluations. And so we've had the assistance of DARPA with that. As you all know, solar cells keep gaining in efficiency each year, and they keep getting more and more efficient, almost 1% a year. And by the time we get to 2030, Brett, we might have some solar cells almost 40% efficient if it follows this trend. And so that only makes the SCP system look even better. For a given power level, the array can be smaller and lighter. Or for a given size, it can be more power. Remember, more power means faster trip times. SCP might even be able to beam power to the surface for use that way. Okay? So there's a lot of flexibility in this particular system. And if array cell efficiency keeps going up, it's only going to get better. The other technology, in addition to arrays, is solar electric propulsion. As we know, there's been a lot of advance in this area recently, the VASMIR, for example. The other good candidate, this is data from AFRL, is a dual-channel Hall thruster. Hall thrusters were invented by the Russians in the 50s. But like the VASMIR, it has this advantage over ion systems. It's variable ISP. So you can dial in an ISP. If you want to spiral out of a gravity well, you like higher thrust, lower ISP. Heliocentric transfer, you like high ISP. And so you can operate this between 1,300 and 5,000 seconds of specific impulse, which is just a measure of thrust versus pound of propellant per second. All right? So that ISP, that efficiency, could be as much as 10 times as high as a chemical like hydrogen system. So SCP is attractive because of its ISP. It has a disadvantage of being low thrust and requiring continuous thrust in spiral out periods. But those can be high power thrusters, 100 to 200 kilowatts per thruster. So my Mars vehicle might get by with 5 or 6 thrusters. Okay? Very reasonable number. Dual mode operation. Now, let me switch gears. I talked about SCP. A very similar vehicle that also is low thrust is nuclear electric propulsion. Fission reactor produces electricity through a Brayton cycle. And this is a multi-megawatt vehicle. The advantage of the NEP is its power is independent of its distance from the sun. The SCP operates well between the Earth and Mars, but not much further than that. The solar flux at Mars is about 40% of what it is at Earth. So between Earth and Mars, you got a good solar flux to work with. But if you're going beyond Mars where there's a lower solar flux, that NTP system has continuous power. Now those are not solar arrays, those are thermal radiators. And so that nuclear reactor, its efficiency requires a lot of area for that excess heat to be radiated. Those are thermal radiators. But that would fly like an SEP, a low thrust system that would that would thrust continuously for days. The GMO program in 2004 was based on NEP technology as well. So some of you know that very well. This is from a Boeing study that we did in 1990. The next is the high thrust, and this is what Brent showed in his DRM 5.0 was a nuclear thermal propulsion fission reactor that heats up hydrogen and ejects it out of the nozzle. It has twice the ISP of a chemical system. The SSME gets about 450. This will get double, about 900. So it has quite a bit more ISP. That's a proven technology that was tested at Jackass Flats, Nevada in the 60s. We understand how to build the fuel rods and the fuel forms to withstand the 2 hours of high temperature operation. So that vehicle, the NTP, is sometimes considered the leading candidate for missions to Mars because it enables short trip times, high thrust, high efficiency. It is dominated conceptually, though, by very large hydrogen propellant tanks because it only uses hydrogen. There's no combustion taking place. It's just a heat exchanger. So they're dominated by high, very large voluminous hydrogen propellant tanks. And if, as Brent says, we're going to spend 600 days on the surface, your Earth return propellant, if it's hydrogen, you've got to keep it cold for 600, 700 days, so it's ready for the Earth return mission. Okay, so that might be a slight disadvantage for the NTP, is keeping the hydrogen cool. But you could run a cooling loop through the fission reactor, produce electric power to run a cryo cooler to keep that hydrogen cool. That'd be a dual mode reactor. And so that is a possibility, though it's another technology addition to the reactor. So that is a candidate you've seen. Matter of fact, let's see if I can get this. The leading candidate in the 1960s was that very thing, NTP. Von Braun's team presented to Congress in 1969, August of 69. That vehicle has the follow-on Apollo, that's on the bottom, for a Mars mission. At the same time, the Boeing company had a similar vehicle. We were doing studies for it. NASA has it, or several other companies, about how to do that mission. Those vehicles are almost primarily tankage sets with engines, and they were a staged approach. So you might have 3 or 4 stages, each with an engine, and after it burns, it drops off. And so multi-stage approach was taken during the 60s. During the 80s, that archetype changed to maybe 1 or 2 engines being reused for the whole mission. All right? What it enables is an opposition class or short stay mission. And Brent, am I out of time? I've got a couple minutes. Got a few minutes. The long stay missions are, you're staying at Mars so that you can wait for an opportune return, low energy return, so you stay 600 days so the planets are realigned so you can come back. Back in the 60s, the Von Braun team favored the short stay opposition missions. All right? In that case, you stay on the surface 30 to 60 days, and you take a longer return back to Earth. It takes more propulsive capabilities to do that. You don't stay as long, but the advantage, if there is an advantage, is the total mission duration is shorter. Perhaps the best opposition trip time you can do Earth to Earth would be about 1.5 years. Okay? With a conjunction mission, it wouldn't be less than 2.1 years, if I've gotten my facts right. So you're saving about 200, 250 days total mission time, not in-space time, total mission time, by doing the opposition mission. It's taking more propellant. You need a Venus swingbound on the way back, so you're getting closer to the sun on the inbound. I don't know, but maybe the Von Braun team was a little bit nervous about having the capability to keep the crew going for 600 days on the surface. Got to land a habitat that's capable of 600 days. Maybe they felt more comfortable with 30 days on the surface for the first mission. That would be easier to do, and then come back and save yourselves over 200 days total mission time. But the thinking since that time is that you can do a lot of useful science for the 600 days. You allow the planets to realign. You have a shorter return, so your transit time is less for the long stay mission. And that's what we're concerned about, the radiation. Now, Mars does have a tenuous atmosphere. Its pressure on the surface is about, what, Dave, 1/100th of sea level. And so there is some radiation attenuation just by being on the surface of Mars. So that is what high thrust enables that. Low thrust does not. The opposition missions have more variation in the delta V requirement. You can see the 2033Ds a year, and there's a lot more variation. And as mission designers, we have a problem. Do we design for the worst case or the easiest case? If you design for the very worst case, you're really going to design a really big vehicle. If you design for the easy case, you're going to get the easier vehicle, but it won't do all missions. So that's always what we have to think about. The other option of the four is a chemical air brake. It's well known, locks hydrogen propulsion. Aero capture at Mars, capture done aerodynamically instead of using propellant, and then propulsive return with chemical stage. That's an illustration. You can see two Earth departure stages, LOX chemical on the left. And then you can see a biconic aeroshell. Inside that is the lander and the Earth return stage. Now the good part about that is that biconic aeroshell that aero captures at Mars may double as the launch shroud. And so you get double use out of that. Its complexity is how do you capture at Mars. And aero capture can be a tricky thing. You have to fly through an entry corridor. And if you're too high, you'll skip out. If you're too low, you'll burn up because the heating rate is too high. So you have to steer the vehicle into an entry corridor. If you stay within the corridor, you take out enough delta V so that you're in a parking orbit. And so typically, at least as I understand it now, this may have changed, the way you control the vehicle is you rotate it around its lift vector. You rotate the lift vector to keep from skipping out or going low. And so we need the G, N, and C to figure out how to do that. It may necessitate a full-scale test before you commit people to it for aero capture. You may have to do a full-scale test without people to make sure that that's going to work. But that's a technology that is required of the chem aero brake. It's not required of the nuclear thermal because its efficiency is high enough, its thermal ISP is high enough that you're able to do it with propulsion because of the ISP. All right, so the advantage and disadvantage of the chemical aero brake would probably be lower development costs because LOX hydrogen, we've been building LOX hydrogen engines since 1959 when they developed the RL-10. That's definitely in hand. You would have the highest initial mass in low Earth orbit, and that's a large part of the mission cost is launching the stuff to LEO. It would have the highest in LEO. SEP would be fully reusable. That would be an advantage for it. The NTP would have lower in LEO than chemical, wouldn't require the development of an aeroshell, and we demonstrated that technology in the 60s. Another approach, and I'm almost done, is a hybrid approach in which you use a chemical stage to depart from L1, do part of your Earth departure burn, and let most of it be done electrically. Then you use chemical to get out of the gravity well of Mars and do the heliocentric electrically. So there's more than one way to do this mission. And I want to give you the idea that there's a variety of ways, and one way is to marry chemical and electrical propulsion to do the mission. Keep the trip times down and use the advantage of the SEP where you can. An initial mission to Mars, you might want to park at Phobos and not land the vehicle. That way you don't have to design the lander for the first mission. You can fly a mission to Phobos, land in the Stickney crater that always faces Mars, use its walls as partial radiation blockage, and then teleoperate real-time rovers and science equipments and pilot plants for in-situ production right there from Phobos at only 6,000 kilometers above the surface. And you can explore Phobos. And that might be an interesting first mission because it's safer, it's easier, you don't have to descend, you don't have to carry the lander with you. And so that might be an initial mission. Follow-on missions can be surface missions, but that would be exciting. Since I'm out of time, I'm going to run on and finish with Mars lander concepts. And here's some recent analysis. A methane lander would have a descent stage, an ascent stage, a crew cabin. And that vehicle might weigh as much as 75 tons when you put in the aeroshell. You take the descent stage, and for the cargo mission, deliver inflatable habitat that the crew would live out of. So the habitat lands first, you check it out, and the crew lands next to it, transitions to live for 600 days on the inflatable habitat. Another inflatable that looks very interesting is an inflatable aeroshell. So here you see the ascent-descent stage a little out before the aeroshell is inflated. When you approach Mars, you inflate that aeroshell. It then aero captures, takes out about 80% of its delta V aerodynamically, and then you jettison the aeroshell. And so those are some landing approaches, but since I'm out of time, I will finish right there.